Hello, if we shine a laser beam through a single slit, one slit only, do you think we can get an interference pattern? Yes, we do. So this is a very typical single slit diffraction pattern. At the center is always this very fat blob. So this fat bright blob at the middle is called the central maximum. At both ends of the central maximum, the dark space here is called the first minimum. Then beyond the first minimum, you see a series of equally spaced bright fringes. They are pretty dim, but they are unmistakable, right? We're looking at an interference pattern. But we shine the lights through one single slit, right? So isn't that just one light wave? So how can one light wave interfere with itself to produce an interference pattern? Maybe it's because the slit is not a point. A slit must always have a certain width b. Maybe we can think of every point along the width of the slit to be a wave source. So in fact, we do not have just one single light ray, but instead we have infinite number of light rays leaving that one slit. So right in front of the single slit, where the diffraction angle theta is 0, all the rays will travel the same distance before they strike the points on the screen, which means all of them basically arrive in phase at that spot P. That's why the single slit diffraction pattern always peaks right at the middle. At this point, every point in the slit arrive in phase. You can't get anything brighter than that. Now, at other diffraction angles along the screen, the rays will be traveling like this towards point P. So there's a path difference between the ray leaving this point of the slit and this point and this point and this point and this point and this point. So now all the light rays from the slit do not arrive in phase on the screen. So obviously they will superpose but not to the same brightness as at the middle. This will explain why the intensity starts to drop towards both sides. So how do we produce the first minimum where the intensity is exactly 0? Let's try this. Let's suppose b sine theta is equals to 1 lambda. That means the ray leaving the slit here and the ray leaving the slit here have a path difference of 1 lambda. Then you might think, oh, so A and C will superpose constructively, right? That's true. But if A and C have a path difference of 1 lambda, that means A and B is the ray leaving from the middle, right smack middle of the slit. That means ray A and ray B will have a path difference of half a lambda, which means A and B will destroy each other cleanly. But so will this ray and this ray, and this ray and this ray, and this ray and this ray, and this ray and this ray. So basically, the top half of the beam destroys the bottom half of the beam completely. Get it? So that's why to calculate the position where the first minimum occurs, we use the formula sine theta 1 is equals to lambda over b. Because that's when b sine theta is equals to 1 lambda, which is the situation we just described earlier. So let me remind you, b is the slit width. So this formula looks a bit similar to the d sine theta is equals to n lambda formula, right? So be careful, in that one, d sine theta, d is the slit separation, the distance between two slits. Whereas here, b is the slit width, the width of one single slit. Also, in d sine theta is equals to n lambda, we are solving for the positions where constructive interference occur, where the bright fringes are. And here, we are actually solving for, you might call it a dark fringe, the position where destructive interference happens. Now in A-level physics, they always like you to calculate the width of the central maximum. To solve that, a lot of students will use this formula, press the sine inverse, get the theta, convert it to radian, and then calculate the tangent ratio so that they get half the width and then times 2 to get the full width. That's a bit tedious because, well, for me, I always just calculate it like that, just 2 lines. For single slits, in practice, the first minimum angle is always very, very small, 1 degree or less. Because the wavelength of visible light is less than 1 micrometer, so even if B is 0.01 mm, it's still like at least 50 times larger than the wavelength. So that guarantees that the first minimum angle theta 1 is always small. So when this angle is small, the straight length W and the arc length are practically the same. So the arc length can be calculated using r theta. So who is my r theta? L times 2 times of theta 1. And then for theta 1, I'm just going to substitute it with lambda over b. I even dropped the sine function here because when theta is small enough, sine theta is theta. And it's that simple. Alright, that's all. Ta-ta!